Welcome back to the third episode in this 8-part series on Bayesian Inference with Stan. In the previous episode, we went through the basic mathematical theory of Bayesian inference. In this episode, we'll put that theory into practice by coding a linear regression using Stan. In the first part of this video, I'll explain how Stan interfaces with a programming language so as to establish a conceptual programming workflow that we'll use for the rest of the series. Next, I'll outline the data, process model, and assumptions that we'll be using for this modeling project. After knowing the data and the conceptual workflow, the next section will concentrate on writing a Stan program from scratch. In this section, we'll go line by line, explaining each piece of code as we go and how it relates to the modeling assumptions, the data, and the theory that we learned in the previous video. Lastly, we'll put it all together and execute our workflow from start to finish. During this part, we'll see how to pass data into our Stan program, sample from the posterior, and generate useful results. As a quick side note, we'll be interfacing with Stan through the R programming language, using RStudio on a Windows 10 machine. If you don't have the prerequisite background in R, check out the links in the description. If you don't want to use R, then Stan interfaces with other languages like Python, MATLAB, Julia, or Stata, but just be aware that the API will be different. You can check out the Stan homepage for support on those languages. All of the code and data that features in this video will be available on my GitHub, which you can access in the description box. It's important to know a bit about all the different moving parts of Stan to give you some intuition about how it mechanically all fits together. Stan works by converting a specially formatted text file, called a Stan program, into an executable program capable of sampling from the posterior. You specify the equation of the posterior in the Stan program using a special Stan syntax. Once this happens, you pass in data, the executable runs and produces a joint posterior table, the results of which can be analyzed. If this sounds complicated, it is. For this reason, Stan has a number of high-level interfaces to make the process much easier. These interfaces are run in languages like R, Python, MATLAB, Julia, or more. The idea behind interfaces is that they expose all of the functionality of the Stan ecosystem to users while abstracting away most of the implementation details. Stan interfaces accept Stan programs as text files, along with data from the environment, convert the Stan program into the executable, run the algorithm, and then return the output back to the environment. In other words, all the processing steps like data wrangling, compilation, sampling, and output interrogation all happen in the same interface language. As such, a typical programming workflow might look something like this. First, you theorize on the model formulation and write your model in a Stan program in a separate .stan file. Next, you load your data into the environment, compile the Stan code, do the sampling, and interrogate the results. The last 4 steps all happen in the same programming environment, so there isn't too much switching back and forth between different technologies. The data we'll be using is the attendance figures from 1,385 matches of professional men's Australian rules football, each row representing a different match. The Y data in this case is the attendance in thousands of people for that particular match. Alongside the Y data, we have 22 X covariates. These are 11 columns indicating which team was the home team for that particular match. A 1 means that it was that team's home game, and a 0 means that it wasn't. 1 column indicating the maximum capacity of the stadium where the match was played in thousands of people. 1 column indicating how many other games are on during that day. 3 columns indicating what time the match started, a choice of Sunday afternoon, Sunday night, or another night. 1 column indicating if the match was played in winter or not. 4 columns indicating the weather conditions, a choice between overcast, stormy, sunny, or windy. And finally, 1 column indicating if the match was a playoff match or not. The process model we'll use will be a linear model. That is, we assume the attendance data can be described as the sum of the numerical value of the covariates times a suitable coefficient for each covariate for that particular match, plus some normally distributed noise. Unlike in episode 2, where we specified the standard deviation of the noise, this noise will have an unknown standard deviation, sigma. In our problem, along with the coefficients, Stan will also have to simultaneously estimate this unknown parameter. I will explain how to extend our mathematical formulation to accommodate sigma as well as all of the coefficients when we start building the Stan code. Finally, let's discuss the assumptions that we'll use. which is really a discussion about the types of priors we'll use. For the intercept and coefficients, we want to choose a prior that reflects three facts. One, that we are ignorant of if a covariate has any relationship with the attendance. Two, if it does have an effect, the biggest order of magnitude is roughly 10, since that's the scale of the output. And lastly, if it does have an effect, we are ignorant of its sign. The best way to describe this is a normal distribution centered at 0 with a standard deviation of 10. Centering at 0 means we are ignorant about the sign. A standard deviation of 10 means effects order of 10 away from the center are plausible, and the normal distribution puts most of the probability mass at 0, reflecting our proposal that we are not biased towards the covariates having any effect at all. For regressions, this type of assumption is quite common when you don't know much about your process, and in the literature you often see this type of assumption referred to as a weakly informative prior. For sigma, we want to choose a prior that reflects two facts. Sigma is a positive value, and it's also the same order of magnitude as the coefficients. One of the most common priors for this situation is a half normal. This is like a normal, but it's been chopped in half, so it only has support in the positive regime. With sigma, we are also being quite weak in our assumptions, but also enforcing a very important property of the parameter, that it must be greater than 0. We know based on the process model construction that standard deviations must be greater than 0, and we will explicitly code that into the posterior. In general, when you know there are certain ranges where it is impossible for the parameter to lie, like for standard deviations, this should be taken care of with our priors. Next, we need to write the stand program that defines the equation of our posterior in terms of our unknown parameters and data. Stand programs are text files with the .stand extension. We'll create a new stand file called matchAttendanceModel.stand. Every stand code is organized into distinct programming blocks, each with a particular responsibility in the Bayesian workflow. There are several types of blocks, but the ones we'll be using here are called the data block, the parameters block, and the model block. These are the most essential blocks to any stand program, and all stand programs will have them, in this exact order. You can create the blocks by writing the block name, followed by an open and closed curly bracket. The stand modeling language is an imperative programming language, meaning that each block, and indeed each statement in them, is evaluated in the order in which they appear in the program. So let's start with the data and parameters block. The stand modeling language is statically typed. This basically means that every variable has to be declared with a particular type. The data and the parameters block are there to declare all of your variables. The data block allows you to declare variables and their types whose values come from the external environment. That is, they are passed in as measured data. The parameters block allows you to declare variables and their types whose values we don't know but want to infer using Bayesian inference. For our problem, the data block will contain the variables representing the attendance data and the covariate data, and the parameters block will consist of the coefficients and sigma. In both blocks, we declare variables by first writing their type and then their identifier name. Let's go ahead and declare the attendance data variable. This will be a vector of length 1385, and we'll give it the name match_attendance. Every line in stand is also ended by a semicolon, so we have to remember that as well. Similarly, we will define the covariate matrix. We know that this is a matrix that consists of 22 columns and 1385 rows. We'll call it X. When it comes to using stand, these variables will assume values that we pass in through the external environment. For those of you used to R or Python, you can think of these like data frames, matrices, or scalars. In the parameters block, we will define three types of parameters. The first will be the coefficients. This is again a vector of length 22, one coefficient for each covariate. We could have individually defined each covariate, but this is much quicker. The next will be a single floating point number, denoted with the type real, corresponding to the intercept term of the linear regression. Lastly, since we're going to be inferring the variance of the linear regression as well, we will declare it as a real number with the name sigma. As discussed previously, we want to learn the distribution of sigma, but also enforce that sigma must be greater than 0. To do this, stand has a really great feature that allows you to constrain the scope of variables. You can do this by typing triangular brackets after the type and passing in lower and upper bounds. In our case, we will constrain sigma to be strictly greater than 0. Now when we sample, all sigma samples will be greater than 0. You can also put constraints in the data block. What happens here is that this acts like a data checking function. For example, I know that the match attendance data has to be greater than 0, so I can enforce that. When I compile my code and eventually pass in the match attendance data, if it's less than 0, an error will occur. Now, just like any other language, it's a poor choice to hardcode in these sizes. We can get around this by also declaring integer variables that define the number of columns and number of rows in our dataset. We can then replace these numbers with those variables. By parameterizing, this will mean that the same stand program will work with more or less covariates and more or less data. Let's move on to the model block. The model block is where we define the equation of the joint posterior probability distribution as a function of both the parameter and data variables. To be clear, these variables come from the declarations we made in the previous two blocks. Anything we haven't declared in these blocks won't be recognized by Stan. Similar to the previous episode, let's start by specifying the prior. Recall that the prior is composed of several sub-equations, one for each unknown parameter that we have. In our example, we have 24 unknown parameters, 22 coefficients, 1 intercept, and 1 variance parameter, so we need to specify 24 sub-equations. We've also reasoned that the priors for each coefficient will be normal with a mean of 0 and a standard deviation of 10, so let's go ahead and code that in. Starting with the intercept, I can specify the sub-equation by writing intercept tilde normal 0, 10. What we are writing here is that the intercept is distributed normally with a mean of 0 and a standard deviation of 10. Remember, the tilde notation is merely a mathematical shorthand. What we are really writing here is the definition of the probability distribution of the intercept parameter before considering the data, that is, its prior. After we've finished writing the prior, we end it with a semicolon and move on to the next unknown parameter. This will be the first coefficient. I can write this by using indexing to access the first element of the coefficient vector and writing its prior. Again, it will be a normal distribution with a mean of 0 and standard deviation of 10. For those of you wondering, Stan indexes start at 1, just like R or MATLAB, and not at 0 like Python. Let's go ahead and do this for all remaining 21 coefficients using indexing. Luckily, Stan has for loops that allows us to write this more compactly. We can use I as the iterator of our for loop and loop through the indices of the coef vector, applying the same prior to each. The for loop syntax is extremely similar to how it works in R. The iterator is one of the few objects in Stan that you don't need to declare before using it. Lastly, we need to put a prior on the sigma term. As specified earlier, we will assume this to be a half-normal distribution. Stan doesn't actually have a half-normal distribution in its library, but since I've already restricted sigma to be greater than 0 in the parameters block, we can simply apply a normal distribution with a mean 0 and standard deviation of 10, and this will, in essence, act like a half-normal. One way to think about this is that the prior distribution will act on the portion of the domain that is available for sampling. At this point, let's stop and review our model so far. So far, I've specified the sub-equations for each of my 24 unknown parameters. For sigma and the intercept, I wrote them as individual statements on separate lines, and for the coefficients I did the same, except I used a for loop as a syntactic shortcut. Remember though that at the end of the day, we have to multiply all these sub-equations together to get the full prior. Luckily, in Stan, that step is taken care of for us in the model block. When the model compiles, each sub-equation that I define in the model block is specified internally, and then all are multiplied together to form the expression of the posterior. At the moment, we have 24 sub-equations that form the prior, so if I were to compile the model now, the resulting posterior equation would have 24 sub-equations in it, and exactly be the prior. In Stan, at no point am I actually required to multiply the sub-equations I define together, because that is implicit in the compilation. So at this point, I've now fully specified the prior, and we can move on to the likelihood. The likelihood is also specified in the model block. This is because statements that form the posterior all get multiplied together during compilation anyway. So, from the point of view of Stan, it makes sense that the place where you specify the prior is the same place where you specify the likelihood. Recall that the likelihood is also composed of several sub-equations, one for each row of data. We have over 1,000 rows of data, so we will definitely need to use our for loop shortcut, but let's start with the first row of data to illustrate the point. The likelihood for any data point is the probability of observing the match attendance that we did for a given set of parameter values and covariate values. We can derive the expression by going back to the definition of our process model. We've assumed that the match attendance, denoted y here, is linearly related to the 22 covariates plus an additional noise term, which is normally distributed with a standard deviation of sigma. We can rewrite this as a probability distribution over y with a mean equal to the linear combination of the coefficients and covariates. If we imagine the coefficients as forming a column vector and the covariates as forming a row vector, then this can be written more compactly as a vector product. In Stan, the syntax for the likelihood mirrors this equation. we can write down the first subequation of the likelihood like this, where match attendance 1 is the first element of the match attendance vector, and x1 is the first row of the covariant matrix. In the last video, we had actually specified a constant value of sigma rather than keeping it as an unknown. So how does sigma as an unknown parameter change our mathematical intuition? Well, essentially it doesn't. Remember, the likelihood is made of subfunctions that are equations of only unknown parameters. The unknown parameters can come from any part of the probability distribution that defines the likelihood. For example, they could be part of functions that form the mean of a normal distribution. They could be part of functions that form the standard deviation of a normal distribution. In fact, they could be any parameter that helps define any parametric probability distribution, and they could even replace the parts where the data goes. This is really useful to infer missing data for particular data points. But regardless of where they come from, if they come together to form a likelihood expression, you can slap an appropriate prior on them, and then add them to a Bayesian inference workflow with no problems. Let's go ahead and write down the rest of the subequations using our for loop trick. We've now fully specified the entire posterior, and we actually have a fully specified stand code. If we compiled this, it would absolutely work and give great results, but just like any other language, there are always ways to optimize and improve what we have written. In Stan, probability statements can also receive vectors or container types as inputs. These can be very useful to replace for loops inside of the model block. In our example, I can replace the for loop defining the priors for each coefs variable with a vector statement on a single line. What's happening here is that every element of the coefs vector is being defined with a prior that is normal 0, 10. In essence, I'm broadcasting the same function across each of the elements. Similarly, I can replace the likelihood for loop with a vectorized version. In this case, the matrix multiplication that happens here results in a vector mean. If that vector mean is input into a normal distribution with a scalar sigma and paired with a vector set of match attendances, this will result in a set of likelihood subequations, each for a particular combination of match attendance, mean, and sigma values. Now that we've written our stand code, it's time to jump into RStudio and execute our workflow. The packages we'll need are dplyr for data wrangling, ggplot2 for graphs, and stats and broom for various other bits and pieces. We'll also need rstan, which is the most common interface for using Stan with R. Stan has a great set of detailed instructions for how to install rstan on their GitHub page, linked in the description. Now that we've got our packages loaded, we load the data into the environment from a CSV. As you can see, the data is a data frame containing 23 columns, 22 for the covariates, and another column for the attendance figures, with 1,385 rows in it. We'll then compile the Stan program we just wrote, using the function stan_model from the rstan package. This will take as input the Stan program file location and output an executable that you can sample from. This step can take up to 1 to 2 minutes. The next step is to sample from the Stan model object to create the joint posterior table. This will first require us to prep the data to pass into our executable. In R, Stan accepts data as a list, so we must create an empty list and populate the elements of that list with the specific names and types that we declared when we wrote the Stan code. In our example, the declared data are an integer for the number of rows, n, another integer for the number of covariates, c, a vector for the attendance data, match attendance, and a matrix of covariate data, x. Now that we've prepped the data, we are ready to sample. We can do this using this sampling function. In the sampling function, we pass in the compiled model object, the data, and some configuration parameters. While there are many configuration parameters when configuring the Stan sampler, the ones that we'll specify here are the most important. These are the number of chains and the number of iterations. The number of chains corresponds to the number of Markov chains that will be used to sample. Remember that when we sample the posterior, we're essentially visiting and recording posterior coordinates in proportion to the value of the posterior at that coordinate. Sequences of visited points are called chains, and each chain will start at a slightly different location. In general, it's useful to have multiple chains to ensure you get good coverage of the posterior. For our case, we'll set the number of chains to be 2. The next thing we need to configure is the number of iterations, which is the number of points that each chain will visit. We'll set this value to be 2,000 points each. You might expect that the output will then contain 4,000 samples, 2,000 for each chain, but Stan actually throws away the first 50% of each chain to allow the sampler to warm up. Therefore, the total number of samples we'll end up with is 2,000. Now, all we need to do is sample. When we execute the function, Stan will start each chain and sample from the posterior. It will give you an indication of how far along it is with the number of visitations printed to the console. After Stan has finished, we're now ready to look at the results. In Stan, the results come in two forms. One is the joint posterior table, which you can get by using the extract function and passing in the fitted object and the parameters you want to inspect. We can see these results as a data frame in a format that exactly resembles the posterior table outlined in the previous episode. The other way to inspect the results is to use the summary function. The summary function works in the same way as extract, except the output is a summarized version of the distribution of the samples. The table shows the mean, the standard deviation, and the various quantiles that define the distribution. Before we look at the results in more detail, we need to check that the sampling worked. Even as powerful as Stan and Hamiltonian Monte Carlo is, it's not foolproof and it can be biased if the model is misspecified. Essentially, sampling can be biased if the chains didn't explore the full region of the posterior. Stan provides three main quantitative diagnostic checks to check for bias sampling. These are R-hats, effective number of samples, and the number of divergent transitions. R-hats are a diagnostic against each parameter, and they can be seen in the summary table. R-hats indicate if the chains are all exploring the same space and are stationary. If all the chains are exploring the same space consistently, then you are likely to have nice sampling, and the R-hat will be less than 1.05 for all parameters. In our example, all R-hats are looking just fine. The number of effective points are also a diagnostic against each parameter. It tells you the number of independent samples in the chain. If the points in the chain visits are too close together, then each successive point won't be independent of the other, which reduces the statistical power of the inferences. For unbiased sampling, you want the number of effective points to be at least 150 for 2,000 samples. In our example, the number of effective samples all seems quite high. The last diagnostic are the number of divergent transitions, which happen on a chain-by-chain basis. They represent the number of times the chain had to restart due to a sampling problem. The more times the chain restarts, the less likely it is to have explored the full space. To get the number of divergent transitions for each chain, you can use the get_sampler_params function and select the divergent flag, taking the sum. What you are really looking for is zero divergences, which is the case for both of our chains. However, in practice, you can probably accept around 10% of samples being divergent without any major issues. Now, while we didn't have to fix anything in our example, it's quite common in practice to run into bias sampling, particularly in the first model iteration. In later episodes, we'll see how to fix bias sampling by tweaking some of the configuration parameters and potentially reparameterizing the model. So now that we are certain our sampling has converged, let's interrogate our results by comparing the distributions we get for each parameter to what we would have inferred by running a frequentist linear regression. We can get the frequentist results by using R's LM function. The result of the linear regression are a table of coefficients with their means and p-values. The coefficients are interpreted as the average increase or decrease in match attendance in thousands of people associated with that covariate. For example, the model expects there to be about 13,500 people more to attend the match if the match is a playoff match versus a regular season match. We can extract the coefficient tables using Broom's tidy function. Now let's look at the marginal distribution of the intercept parameter from the joint posterior table from Stan. Remember, all we need to do is isolate that column in the posterior table and draw its histogram. For this we'll use ggplot. We can see that the distribution is around 23 to 35. This means that every value in this range is a plausible value of the intercept after seeing the data, with the most plausible values ranging from 29 to 31. If we overlay the value of the frequentist intercept, we can see a clear overlap, but the frequentist value isn't in the middle of the credible interval. The reason this occurs is because the prior is pulling the inferences closer to zero. This is because we introduced a prior that was centered around zero and really highlights how the prior is acting like another piece of information the model considers when it determines plausibility levels. In the end, this means that coefficient values closer to zero are more consistent with the data and the prior than with just the data alone. Without the prior, as in the frequentist version, point inferences become more extreme than we would otherwise get. Introducing a prior that pulls inferences towards zero is known as regularization, and it's a good technique to avoid extreme inferences or overfitting. We can do the same thing with the coefficient parameters. Rather than drawing a histogram for each parameter, I'm going to draw a line segment representing the 95% credible interval. That is a line going from the 2.5th percentile to the 97.5th percentile. I'll draw this line segment for each one of the coefficients and order them in descending order. We can clearly see the effect size of each variable, just like in the frequentist model. Being a playoff match has the highest correlation with more attendance. Another interesting result are the impact of the weather. When the match is experiencing poor weather, storms or overcast conditions, this tends to reduce match attendance by about 1,000 to 5,000 people. However, when the weather is windy, it's highly uncertain what the correlation with attendance is. Just like with the intercept, if we overlay the value of the frequentist coefficients in red, we get a perfect overlap of inferences. But again, all of the frequentist estimates are slightly more extreme than the middle of the Bayesian credible interval. Again, this highlights the influence that the prior has in regularizing the inferences. At this point, there's probably lots more we could do, but I'll stop here and leave two exercises open to help you consolidate your learning. The first is to compare the values of sigma for both the standard distribution and the frequentist value. The second will be to compare the predictions made by the stand model to the actual attendances, using the simulation technique that we discussed in the previous episode. Have a go at both of these, and if you want to check your answers, both of my solutions will be on my GitHub. We're now at the end of the third episode of this course. At this point, you have enough tools to go and use STAN for your own real-life modeling projects, so it would be perfectly reasonable to end the course here. However, if you want to stick around, in the next 5 episodes we'll be extending what we've learned in the last 3 to do more advanced and interesting statistical modeling. As always, if you have any questions, feel free to post them in the comments below and I'll try my best to get to each of them. If you like the video, give it a thumbs up, subscribe and turn on the notification bell, and I'll see you in the next episode.